So, very fast. So let's get started on this first talk of this session. And I am very pleased to honor here Vyjayanthi Chari, who was my colleague for a long time in Tata Institute. We shared office for a few years, many years. So I'm very pleased to introduce her. And her title is long one, categorification from alternating snake models, Q characters, and determinantal formula. So that's.
Thank you, Charlotte. And thank you, Milan and Emily, for working together. It's very nice and comfortable. I'm very happy to be here. So, okay, so I will begin with some motivation for the kind of thing we're going to talk about. So basically, it comes from the notion of monoidal categorification. And this was introduced by Hernandez and Leclerc. So what they proved was that there was a nice category of modules that I'm going to denote as CZ. So these are finite dimensional modules for the quantum affine algebra. And it's a tensor category. So you can look at its Rosen degree. And they showed that this had the structure of a cluster algebra. So this is isomorphic to a certain cluster algebra, which I'm not going to write down. An infinite quiver. And then they proved that there was this isomorphism of algebras. And it sends the initial seed to a well-known family of modules here, to a subfamily of that, to some Kirill Brashitikin modules. So I'll explain all this in a minute. Okay. And they conjectured, so they didn't say anything about the other cluster variables, but they conjectured that the cluster monomials mapped to irreducible representations. This was a conjecture, and then it was a theorem. And then the theorem was due to follow from the work of Shin and Kashiwara, Kim, Ho, and Park. That it was actually true that cluster monomials map to irreducible representations. A very fidgety moment. So,
will you be able to tell us what this subscript Z stands for?
Integers, I'm going to tell you in a minute. So, yeah. I'm going to define it. I'm going to be more precise in a minute, but I just want to talk about the general thing. Okay, so this in this category, one knows what has an index set for all the irreducible representations. Okay, what this theorem doesn't tell you is what the cluster monomial, what kind of irreducible representation the cluster monomial maps. So you have no idea what the images are in some. So that's partly the motivation. So there are many questions. So many questions remain unanswered. So what irreducible representations are you picking up? And here there's a notion of what are called real and imaginary modules. So what this means, so you say a module is real if its tensor square is irreducible. Sorry, is real if, so V is real if the tensor square is irreducible. And you say it's imaginary otherwise. And since this is an infinite quiver, you know that cluster monomials don't span this algebra, so the image must contain imaginary modules. So what imaginary modules lie in the image. And how is, how are they somehow related to the cluster variables? And then, of course, one wants to know, what nice representation theoretic properties can you find? Do these images have? So part of the difficulty in answering all these questions is that you don't know anything about the image because all you know, that the initial seed mapped to something very nice. You can get everything else by cluster mutations. Cluster mutations get out of hand very quickly. So you don't have much hold on what the images are. And so what I want to explain today is what modules you do not lie in the image and some other modules which hopefully will lie in the image. So the snake modules will lie in the image and the alternating snakes, we don't know if they are in the image or not. So what I want to talk about is then therefore real irreducible representations. Okay. And also prime. So let me tell you what prime means. So when you say the cluster monomials, the cluster monomials are sort of cluster monomials go to irreducible modules and so cluster variables. So they're indivisible. And so in this context, they go to what I call prime representations, which just means that you can't factor, if you have the image of a cluster variable can't be factored, it's written as a tensor product of two irreducible representations. 0.5 hours per second. Okay. So, and then I want to show you that in some cases, one has a nice wild character type form. So that's the goal of the talk. So let me just set up some standard notation. So I'm only going to be working with SLN plus 1. Okay, so this is where life is nicest. And so UQ-SLN plus 1 is going to be the quantum group associated to the algebra. So I'm not going to write down as write down the relation completely, but you have generated EI, FI, and EI plus or minus 1, where I goes from 1 to n, and they satisfy some nice relations. So, for instance, you have a relation which will look like EI bracket Sj, delta ij, minus so this is like an SL2 relation. Have some other natural ones, sorry. And then the quantum affine algebra, so UQ hat, SLN plus 1. So I'm just going to write UQ and UQ hat from now on. So this will have infinitely many generators. So you'll have for every node of the Lincoln diagram and every integer r and phi ir with some horrible relations. Yeah.
So this is not the affine one, this is the loop algebra.
Yeah, this is going to be the loop algebra because all finite dimensional representations are.
Yeah.
So this is the affine modulo the center. Okay, so yeah. So both these algebras, so UQ is a subalgebra of UQ hat. And in fact, they're both subalgebras and it's in fact a Hopf subalgebra. So those are the algebras one is interested in. And so now let me tell you a bit about the representation theory. So for UQ, since we're working with SLN plus one, the irreducible representations are just given by partitions. Lambda one greater than or equal to lambda n plus one greater than or equal to 0, okay? Or equally by Young diagrams. And the fundamental weight, the ith fundamental weight, is just the column of length I, of I. Okay, so this is the column. So I'm not sure how far down I'm allowed to write. So go. Okay. And the other, so these are the irreducible representations, and then any finite dimensional representation is completely reducible. So this is a semi-simple category. And the third property is that yeah, so tensor products are given by the little symbol. So this is all well known. Now, when you go to UQ hat, things become a bit different. So I should, yes, so there's one thing I should say. We have, in the case of FLN plus one, which is very special, we have evaluation maps, UQ hat to UQ. For every, I'm always working with, Q is never a root of unity. And so I always have these evaluation maps, which goes from UQ hat to UQ. So you can pull back any representation of UQ to UQ hat. In particular, you could pull back, so pulling back, we can pull back fundamental representation. So let's just, I'm not going to write V omega I, I'm just going to draw this column I, and then you'll denote that by, let's say, omega IA, which will represent, so you take the column and you take, so it's indexed by the column and there's scalar A. So for the rest of the talk, I'm going to write this particular fundamental weight. I'm going to think of it as sort of starting at A and going up to A plus I. So as a column back those labels. And then the irreducible representations of UQ hat, so this is all resolved correctly, are in bijective correspondence with the free abelian monoid generated by these omega IA. So, in other words, so if you take an irreducible representation of SLN, SLN plus one, and let's say you look at this Young diagram, and what you're doing is for every column, you're taking a different, but you could be taking a different parameter. So that's the idea. And you get all these irreducible representations like this. However, this is not a semi-simple category. The dry one is listed there. So I'll come back. This is not a semi-simple category. And the tensor product is apart from, well, in general, apart from yours. I haven't talked about characters over here. Of course, one knows that the characters are given by. So I just the eigenspaces of the content. Okay. And here we have the notion of a Q character. And this was introduced by Frenkel and Riverside. So we have these generators on here, PIR. So the PIRs are commutative, and so we write V as a direct sum. So of V omega, where omega is in P. P is my group. P is the group. And these V omegas are generalized eigenspaces for the action of CIR. So the Q character then is just so what they proved was that you had an injective ring homomorphism which went from the growth degree. I've told you what, so let me tell you what CZ is in a minute, to polynomial rings and variables in infinitely many variables, and it sends an irreducible representation to the summation, the usual notion of character. So you take the group algebra and then do that. So the growth ring is commutative, although the category the tensor product is not commutative. Okay. So this is the theorem of Frenkel and Reshetkin. And to answer your question about what CZ is, so we take P plus D. So we take P plus D to be just the things generated by omega IA, where A is going to be reduced. And CZ then will be the irreducible modules which are indexed by elements of P. Those are the modules that live in the Hernandez Leclerc.
But A is an integer,
A is an integer.
but you want non-zero integer, I suppose.
Yes, no. No, because technically this should be omega I cubed to the A.
Okay.
So I don't want to write cube to the A or something. Okay, so
Q is generally, right? Q is not, what is Q?
Q is a complex, non-zero complex. I'm working on the C.
Okay. But generally.
Yeah, it's not a root of unity.
Not a root of.
Not a root. Yeah. Okay, so let us look at how let's look at the tensor structure of this story. So supposing we take, so I have my so let me give you an example. So supposing I take a column of height 3 and I put it at A and I have these labels for it. So this is A and this is A plus 3. And I want to tensor it with, let's say, B and B plus 2. Right. So basically what you do is you slide them together, and if you get a skew diagram, then the tensor product is going to be reducible, and otherwise it's going to be irreducible. So this tensor product is irreducible unless, in this case, let's see, A less than B, less than or equal to B plus A plus 3, less than B plus 2. So that's because I need this. So on the other hand, if I have this picture, so now let me draw it more carefully. So if I have this picture, so this is supposed to be in the same line. When I slide them together, I get a skew diagram. So this is A plus 2. Yeah. And this is A plus 4. So I get the skew-Young diagram. This one is the same thing as A plus 3. This goes from A plus 2, A plus 4. And then if this is not semi-simple, but it's Jordan Holder series, what it's going to look like is now this you have only 2 components, and it will look like the following. We will have 4 and
So when you say skew diagram, you mean connect.
in this case, I mean connected. Yeah, it doesn't have to be always connected, but in this case, it should be connected. Yeah. If it's not connected, it can be irreducible.
It will be irreducible?
Yes.
Okay.
That's how. Yeah.
Okay.
So I mean, you could have it.
No.
Yeah.
This is an equality in the growth and degree.
This is an equality in the growth and degree. Yeah, I'm going to write it as direct sums. Equalities.
What are the subscripts in those?
So this just means I'm taking a column of height 3
No,
with this.
I mean, on the other factors, what are these?
Oh, this will be the same. So this will go A to A plus 4. And this will be A plus 2 to A plus. You just slide over as much as you can. And then it just splits off.
It is different from B, isn't it irreducible?
No, Shravan, that's only in the classical case.
Oh, what is the class? Correct.
Yeah. So let me give you one more example, and then I'll show you how it connects up with the class.
And the last thing is direct sum of the.
It's sum. It's a Jordan, this is a Jordan, these are the two Jordan Holder components of this tensor product.
And the last thing is sum.
This is tensor.
After.
This is the tensor of these two representations.
But that tensor product should be reducible,
This tensor product will be irreducible.
or
Yes.
that it's not a student.
Yes. So I'm going to state a precise condition after I've done these examples. Okay. All right. And then you can do another. So here we are sort of just. So you can do another thing, right? And still get a nice Young diagram, which will be to just take the box up there. Right? Just so it should be roughly the same length. It's like this. Right? So this is A to A plus 3. And then this is A plus 3 to A plus 4. So I should have two boxes. So A plus 5, right? And now what does this picture look like? My things will look like, so you have I'll have this Young diagram again. And the next bit will just be 5 boxes. So this will go from A to A plus 5. Okay. So you slide it over, maybe write down all the Young diagrams that you can get. Okay. So let's compare this with the classical decomposition, right? If you're working in UQSLN, then SLN.
Can I just clarify if the second one was higher,
Yeah,
then what would you get? So
it would be irreducible.
what would its name be? How would you?
It would just be the product of these two things. So this one I would call omega 3 A plus 3, right? And this I would call omega A plus 3 A plus 5, right? And if these two hadn't matched up, for instance, then it would just be the label would just be the product of those two things. The label of the irreducible is always the product.
And we are in the integral case. A and B and
It will be an integral.
are integral.
This will all work without integral, but okay. So now suppose if you're just doing this in SLN plus 1, right? And you're doing the same decomposition. So what does it look like then? Then that is this Young diagram. Okay? And then you have a thing of length 4. And then you have a thing of length 5. Okay. Yeah.
So this is what the usual.
This is the classical thing.
Classical.
Exactly. Right.
None fine.
Yeah.
Right.
So of course, this as a representation, as SLN plus 1 representation, these are all the same, the left hand side. Right? Because this is just the evaluation representation, which is a book. Okay. But when you look at it when you look at the Jordan Holder components, they're quite different. Okay. So the point here is that this is an evaluation representation, but this is not. Because the second representation, right, is equal to the sum of these. This one's left out. Yeah.
So at the equal to 1 limit, you have this evaluation module. So
Yeah.
I guess
You always have, sorry.
there's a similar rule, I guess, for the evaluation.
In the class, you mean so for UG, in the classical case, if you take the same parameters, there's no power of Q to fiddle with. So if you take the same parameter, you're going to get the same decomposition. It's not so subtle. So the power of Q makes it all very subtle. So it's really picking out different decompositions of this. Yes. Yes. Okay, so what is the general rule? So I should say that this way of writing things is really motivated by mean, I've really stolen the language of, that appears in fairly book to the work of Lockheed and Vineyard, where they do very similar kinds of problems, but they use relative schema segments. That's what I'm really thinking of these things over here. Yeah. So you could think of this, so you could, for instance, this omega 3, A plus 3, you could think of it as a single multi-segment, A plus 3. Right?
One sense, I mean, keep on saying.
So neither of them are here, so neither of them are here, so I can but okay, yes, but thank you. And then the other one will be, if I take tensor product, then I could have something like A plus 3, A plus 5. So it's a very convenient way to think of, instead of working with Drift-out polynomials, it's much more convenient to work with this kind of notation.
So what is the notation A plus 3? Same like omega A plus 3.
Exactly. So
Shorthand,
you think of this as an interval.
The sequence of integers.
So what is the rule? So now supposing the then the proposition is the following. So supposing I take a tensor product of two fundamentals. So then this is reducible if and only if. So one of the following holds. You have to have A less than B less than or equal to A plus I less than B plus J. So that means you patch them together as a skew diagram, or the other way around, B less than A less than B plus J.
So this is something like interlacing property.
Exactly. And then so this is reducible, and then it has two Jordan-Holder components. Okay, which I'm going to write as a short exact sequence. Okay, so you'll have a non-split short exact sequence. Okay, and then I'm going to assume the first hold, so A less than B. So then the non-split short exact sequence will look like, so you take the skew-Young diagram, let's say A, B, A plus I, B plus J. In the middle, you take the tensor product. And in the quotient, you take this long thing. You go from A to B plus J, tensor with B to A plus I. So you're exchanging.
This is how parabolic reduction behaves.
Exactly, but here it's proper tensor products because we're in a half-half.
So this is the exact sequence.
Yeah.
And
It's a
the
non-split.
last one is irreducible.
Yeah, they both, yeah, exactly.
Yeah, the
This is
last
the
one,
normal.
first one are irreducible.
Exactly.
But I mean, this is how algebra, the whole person that you construct, right? The ecology of.
That's right. But every SLN is a half algebra. UQ of SLN, UQ of SLN plus 1, they're all half. SLN plus 1. So you don't need to do this to reach. So this is a non-split short exact sequence. And this is the first, so this is sort of an example of a cluster mutation. So you can think of this. So this proposition can be reformulated by saying that this is a cluster algebra. So we have a cluster algebra of type A1 with 3 frozen variables, possibly 3, because some of these columns might vanish. 3 frozen variables. So you, in the center, in the middle, I mean, the non-frozen thing will correspond to, let's say, this A to A plus I. And then you'll have these 3 frozen things. Right, so this one, the skew diagram, and actually 2 frozen, maybe, yes, 2 frozen. And then you'll have the other one, the long one. And yeah, why did I have 3 in my notes? Yeah, better look at this. It's slightly wrong. Yes, of course. That's right. So no, I think I do want 3. Yeah, so this one is just this long one, and then this is the short one. Okay. And these two are well done, yeah, and then let's say this arrow goes out, and then these two arrows will go in. Right, so then, and then the first mutation will be the other one, which is B plus K. And then you have the same chosen, but the arrows will go the other way. So this is so this very elementary thing gives you a classical browser type A1.
So it's always, if it's reducible, it will have only two components.
Exactly.
So if we're multi-site with an affine Hecke algebra, it's sensitive to the order that they're censored in,
Yeah.
but that's not true.
And this is true over here. You notice that I said I'm going to assume A is less than B over here. And if you take A greater than B, then the order of the short things will change. So the solver will become the headlands. So it is sensitive. Okay,
Just to clarify, the skew diagram is also irreducible.
the skew diagram is also irreducible, exactly. Yeah. So the skew diagram will always sort of contain the SLM module coming from the Young diagram and the plot. Okay. Okay, so since it's a non-semi-simple category, one has a notion of standard modules. And it's a sort of old result due to and myself, so independently, it goes back a long time, which says that so the standard modules in this case are precisely tensor products of columns. So let's say A1, and then you have A1 plus I1, and then you tensor up with AK plus IK. And the only condition you need then is that A1 is, let's say, maybe greater than or equal to A2, greater than or equal to. So if you order your columns so that these numbers are decreasing, then you get, and you take the tensor product with the standard module. So what are the properties? It's indecomposable. It has simple head. And the head will just be the product of all these things. Yeah. So, yeah.
How does this depend on n?
So you only allow columns of length.
But if you just, it's stable, right?
That's right. So after a point, it will work for all that.
So.
You might as well work in big enough n.
Yeah, okay.
Yeah.
Then it is following exactly the same thing as this ref of
Exactly.
to 8 for all n.
Yeah. So you can also work within a fixed algebra, but if you work, and then you just have to understand that some boxes don't exist, right? So if you're only in this picture, if you're only in SL4 or something, then you don't have a column of length 5.
Yeah, yeah.
So that's the understanding. But so you can write everything in general terms. Yeah. Okay. So these standard modules are simple, and in fact, remarkably little is known about maps between these standard modules. But but recently, what Brito and I proved. So these standard modules have been around for a long time, but it's been hard to work with them in the language of neutral polynomial. But in this language, it's much easier. So I won't state the club, but I'll just show you that it looks exactly like.
So this is the definition of a standard module, right?
This is not quite the definition of a standard module. The standard module is given like a Verma module by generalizing relations, for instance.
I see. And then the
And
theorem
then the
is that
theorem is that size move.
this is exact.
And Nakajima had another way, geometric way of talking about standard modules, which I don't know, but again, they're all the same. And so then the theorem as we proved, and it's only known in SLR, is that if you take, if you take two standard modules, let me call them W and W prime, then this dimension is less than or equal to 1. Any non-zero map is injected. And one can describe, and one can say precisely when this space is 1. Basically, it's some sort of interchange of coordinates. It's a bit hard to say this. But this is exactly like Bauer modules. This is what one would expect from if you think that standard modules should be universal objects. And if n is large enough, for n large enough,
What did you write?
standard modules are simple circle as well.
Sorry, what did you write? I1?
And one can say precisely when the home space is one dimensional.
I see. And do you also know the higher X information?
No, I don't know any information beyond this at this point. This was done in 2025. So,
Okay, I see. Okay.
so it's taking a long time for us to understand home spaces.
Okay.
The analog in that case, that's known by Bertie Lewinsky.
I don't know.
So sorry, in the p-adic case.
Yes.
One can say more about X groups and so on using theory of derivatives. So I mean, what you're describing seems like there should also be a theory of derivatives.
Yeah, I'm sure there is, but if you're trying to prove something low, I mean, I'm not saying that one can't say anything, I'm just saying I don't know what it is at this point. Right? I mean, I also have to translate all this language, and I'm trying to do things inside the quantum affine set. Okay, and so when n is sufficiently large, one can also prove that the circle is true. So, all right. I'm going to run out of time, but anyway, so let me just.
So, no, 1 minute.
Yes.
Sorry. Any sufficiently large means what? Compared to W and W prime?
No, compared to, compared to these, yeah, exactly. So W and W prime will have some like intervals, right? So, so you have to somehow.
So this n should be large compared to some W and W prime.
Exactly. Okay. Okay, so let me briefly tell you about Q characters. And so I want to tell you Q characters in a tableau form. So what is a character? If you just take a column of length I, right? So I'm going to do something slightly unorthodox, but it just is helpful for me, which I'm going to fill this with. So by filling here, I will mean that I'm going to fill with I up to the integers I up to n plus 1, and it's going to be weekly increase. Weekly increasing.
No, is this I or K?
This is I. So this is just a column of length I.
Ah.
Here I'm working with just SLN plus 1.
Oh, I see.
QQ SLN plus 1 if you like. Okay. And then the character is just sum over all these fillings. Okay, in the case of classical case or in the QQSLN plus 1. So I want to now tell you how I want to think of Q characters in the so now if I'm doing A to A plus I. So I'm going to take a filling which depends on A, obviously. And so the filling is going to go from A plus I. So the fillings will go from A plus I up to A plus n plus 1. And let's supposing I've done this filling and I've got and weekly increasing. And let's supposing I've done this filling and this is C1, C2, and CI. So the associated character, so the Q monomial, will be the following. So it will be, so if I look at this A plus I look at the number below it, so that's C1. It's very perverse. Let me call this CI. This is C1. So it will be A plus I, CI. But when I come down here, so A plus I minus 1, right? This is A plus I minus 1. And now I have something above it and I have something below it. So when I take the one above it, I'm going to write CI inverse. And when I take the one below it, I'm going to write CI minus. So this is C1. What did I decide? This is CI. This is CI minus 1. Okay. And here I'm going to write CI minus 1. C I minus.
Oh, when you say weekly increase on it, are you following the correlation convection that is actually weekly increasing by walk down?
Yeah. Yes. Okay, and then I continue. And then when I come to the last one, I only have something above it. So I will get omega A C1 inverse for determinants. So from my filling, I can read off a particular element of my abelian group, and then my character, my Q character, is just the sum of their own fillings. Oh, yeah. It's just the classical character. But Q characters are much more refined than regular characters. So let me just make a remark that if you're doing FL3, for instance, and you're working with the adjoint representation, then so you can. Oh, it's okay. Yeah. Okay. So Q characters are found refined. So let me just explain this in. So let's look at this. So remember, we have this evaluation representation, the lambda, right? And let's suppose the lambda was a diagram like this. Yeah. Then what Presley and I proved sometime in the 90s was that you should really be thinking of this. So if you want to put the parameters correctly, then you should be thinking of it like this. So let's say 0 and 3, and then this one you bump up 1, and then this one you bump up 1. This is the diagram that you should be taking. So this is 0 to 3, this is 2 to 4, and then this is 4 to 5. So this is what the skew diagram of evaluation representation is. And then what Mukhin and Young did, and they call them snake modules. In the theoretic literature, they call ladder modules, and actually they look more like ladders than snake when you use the language. So the result of Mukhin and Young. So they just took modules which are as follows. So they were all skew Young diagrams. They could be anything you like. And you continue in this way. And they computed the Q character of these modules. And the Q character can be given in terms of fillings. So the Q character. So let me just tell you about the fillings for this. In each column, you take the appropriate filling. So that, let's say this is going from 0 to 4. And this is 5, 6, 7, 8. So in each column, you take the filling appropriate to this parameter. So it will be here, it will be from 4 to, I don't know what rank I'm working in. So 4, let's say 4 plus m plus 1, whatever the rank is. And you fill it with that. And the only condition that you need, so remember for semi-standard tableaus, you need it to be increasing along rows, right? But the only condition you need over here is that all these diagonal entries should be increasing. So let's call this A, B, C, D, E, and F. So you need that A is less than B, you need C less than D, E less than F, and then you continue with each block. Okay. And then it's almost trivial when you put it all together to see that every weight space is one dimensional. So all the fillings give you distinct characters, Q characters, distinct human numbers. Which is of course very different from what happens when you work with the evaluation module in the standard.
So the evaluation module for the quantum SLN or affine quantum SLN is always just one dimensional weight spaces.
Yeah. I mean, for more complicated pictures like this as well, yes. That's a snake in lambda. So they're like minuscule representations.
Yeah, so they are like minuscule. For any lambda, it's not.
Yeah.
And any evaluation A.
Any lambda, you start with any evaluation A, or you can take more complicated parameters like this. And as long as you impose these kinds of conditions on the fillings, right? So along the diagonals, as it were, you want them to be increasing.
But that's a recipe. But I'm saying that if you take any
Yeah.
lambda and any A,
Yeah.
the weight spaces are one dimensional.
But if it's an evaluation module.
Yeah. No, I'm not only.
Yeah. That's a special case.
So that's very, very different from the non-quantum situation.
I'm not disputing.
No.
Yeah, so that's what makes the subject interesting. Okay, so in the last few minutes, okay, so these are the sort of nicely understood modules. And then in the work of Hernandez and Leclerc in their original paper, where they talked about the category C1. So in this language, they have a module of this kind. So let's say this goes from, I want to be careful. So this goes from -1 to 2. And then they have a module which looks like this, okay, which will go from 1 to 3. And then you have another module. So this is skew diagrams, right? Every pair is a skew diagram glued together, but the whole thing can never be made into a skew Young diagram, the way it's. And this is a cluster variable. In that equivalent. So what this is in some ways is a sort of concatenation of snake modules in different orders. So this is an example of what we call an alternating snake module. And so what you do is you take a collection, you take say a collection of let's do this small example. Okay, so you go up a little bit and then you start going down a little bit. And then you start going up again. Okay, so it looks a bit like that. So it's like you're going up a ladder, coming down, going up the next ladder, and so on. And you have to impose some restrictions, and then we prove that this alternating snake mod, so there's a theorem again in 2025. Is that alternating snake modules are real? So the tensor square is irreducible. And they have an absolutely beautiful determinantal formula. So and there exists a matrix, let's say A, which will depend on the alternating snake. And this matrix will have entries in the growth and decrease. And the entries will always be, so it'll either be a column or zero. Those are the only possible entries that you're allowed.
No, A+1.
A plus I.
A+I, yeah.
So it can vary what entries, what fundamental representations can appear. And if you look at the determinant of this matrix, Okay, then the determinant of this matrix is really going to be an alternating linear sum of the y modules, standard modules, and that's going to be the equal to the growth of the class of the irreducible module. Okay, so you can, at least you can write the class of this module as another way to say that is to, you can write this as summation minus 1 raised to sigma. And then sigma will be some suitable subset of R, I think R is, and then there will be some Y modules depending on this. Standard modules depending on this. And you can make, so in the tech algebra we mentioned a few times, there's another way to, so in particular, you can do your evaluations modules in this way, right? And so let me just conclude with one comment. So there's this Arakawa stuff. So Arakawa has some functors. Okay, so it has functors which are defined for every dominant. Well, I'm going to only worry about it being defined for dominant integral weights. And this will go from the category of representations of GLR to representations of the affine Hecke algebra. Actually, it goes to degenerate affine, but it doesn't really matter. So HL squared. Okay. So there's a dependence on L. Okay. And these representations are equivalent to some subcategory of representations of the quantum affine algebra. There's also a functor in this direction. So this is a Schur-Weyl duality statement that you have a map functor which takes you from these finite dimensional. Actually, it's functors for that. Okay. So if you take and then so for suitable and then this functor is exact. This functor is very nicely behaved. It takes induced products to tensor products. Okay, so it preserves the multiplication as it were, and then this functor F lambda, it maps a Weyl module to the standard module in the affine method, and the standard module goes to to the standard here in the quantum affine. So for suitable choices of lambda and mu, Arakawa's functor, together with the functor that Andrew and I defined over here, takes a Weyl module from the category O to the standard module, which is finite dimensional, in the category of representations for quantum affine. And it sends, again, under suitable conditions, it will send the irreducible to the irreducible. In the case when this irreducible is finite dimensional, what you get the snake module. Yeah. Okay. In the case when it's irreducible, you get the snake modules. Sometimes when you take Weyl modules, you get these alternatives. So there's this nice connection with completely classical things. And that's it. Sorry.
Okay, anybody, any questions, comments? Yeah. Let's
Okay, so the result of the Hernandez Leclerc, so it's the cluster variable is only for that variable, that type of that picture, yeah. Or is it for any general alternatives?
For any general alternative sake, we don't know that it's a cluster variable yet.
Okay, and then
We don't know, but snake modules, you do know are cluster variables. You can, so John Wrong and so on wrote down a list of mutations which will take you from the initial seed with snake.
and one quick another question is, you also mentioned the proposition that helps actually do the tensor product, the fundamental elements like just few of them. And it kind of sounds like you just have to slide it diagonal as I make a position of that. Then just my quick question is, this same rule or same property will hold if there's actually more than one tensor product?
It's very
Oh,
very hard to because
because it's telling it's
Yeah,
natural to imagine that, yeah, so.
it's suggestive. But I only started thinking of these things in this way very recently, so I don't know the answers. But it did.
Can you say something about the seeds where these cluster variables belong? What is the combinatorics of the rest of the cluster variables in a given seed? Like you show the slide, like the snake modules, and probably they belong to seeds where all the modules are snake modules.
No, I don't. No, I'm not entirely sure whether the other modules in that are snake.
Oh, they're even non-snake models in the same seats.
It's possible, I would think. I don't know. Yeah, because even in this, even in the category C1, you will have a snake module and this module.
Okay,
This,
so,
I mean, this is a cluster variable, and then you'll also have fundamental representations in that.
so there are seats that consist entirely of alternating snake
No.
models.
I
No,
don't know that.
no.
None of that. I don't think so. No. It's very abstract, like this. I don't.
Okay, anybody else, any other question? Actually, so this determinant formula you wrote down,
Yeah.
that's only for the snake modules or for arbitrary?
Those are for alternating snake modules.
Oh,
Or any particular snake. So for snake modules, it was done in the work of Mingus and Leclerc, right? And snake modules, yeah. Snake modules come from these, that's really a BG, just transfer of BGG information.
And how much is there some theory, part of this theory for other G's, other affine G's?
There's a lot of the theory for other affine, but not the theory of snakes. So for snakes, yeah, everything is more difficult for other G's. Because you don't have evaluation representations, that's the beginning, that's the beginning point. But so there are many things that you can do, so evaluation representations are replaced by so-called minimal affinizer. But it's all very hard.
Okay, let's see. Is there any other question, comment? Okay, so let's try this.